do this, not that. This one. Okay, should be going now. Okay. Let's give you guys a sec to get in here. Alrighty, so today we are going to continue on talking about our Diels-Alder reaction, which we saw was a cycloaddition reaction. That means that we're going to be combining a diene and a dienophile, and they're going to make a ring together. So remember, this is a 4+2 cycloaddition. We're putting a 4-electron system with a 2-electron system, making a nice ring there. What's interesting to note is that you can't just use any plain diene and dienophile. For example, if you were to try this one, you'd get no reaction. The reason this doesn't happen is because we're going to see that this diene is locked as S-trans. So those two double bonds are trans to each other, right? They are on opposite sides of that single bond in between them. And that single bond can't rotate because it is in a ring. Remember, normally a single bond can rotate, right? And so with a normal alkene, yeah, we can just go ahead and throw it into S-cis conformation. But with something like this, where it's locked in one position or another, we're going to see that that will greatly affect the reactivity of your diene towards a Diels-Alder reaction. So we're going to see here that with something like this that is permanently in the trans conformation will never react for Diels-Alder. And the reason for that is because we need, for a Diels-Alder, we typically draw it like this, right? We need two carbons to be close to each other. Or rather, 4 carbons, a set of 2, right? So we're going to need these carbons to be close enough to each other that they're going to be able to react together. And so that can only... You got a question? Or maybe just some residual noise? Okay, cool. We need those 2 carbons to be close enough... those 4 carbons to be close enough to each other in order to react simultaneously. So remember, this is a concerted reaction, so everything does happen in one step. So if it's in trans conformation, you try to do that, there's really no way for us to connect these 2 carbons down here. So that's just not going to happen. So if we want our cycloaddition to happen, we're going to need this to be in the S-cis conformation. So something that's locked in S-trans is going to be problematic. Remember, though, that these two, as drawn, are the same molecule, right? They can just rotate. They're just rotamers of each other. These two are identical to each other. So we don't have to worry about those. It can adopt the S-cis conformation as it rotates, and once it does so, it can react. But this ring 1, it's locked as trans. It's never going to react because it can't adopt the cis conformation. On the other hand, we have some dienes, like this little dude here, Cyclopentadiene. This one is locked in S-cis. And so we're going to see that this is actually extremely reactive towards Diels-Alder. To a Diels-Alder reaction. And because it's locked in that cis conformation. We know that generally at most temperatures, there's a roughly, about 1 to 50 ratio of cis to trans. So most of them do exist as trans for steric reasons. And, eventually they'll rotate into cis and then they can react. Cyclopentadiene is locked in the S-cis conformation. And as a result, will be very happy to react. And in fact, it actually reacts so quickly that if you just have a jar of it by itself, we're going to see that if you just take two cyclopentadiene molecules, you're going to end up reacting them just by itself. At room temperature, they'll just Diels-Alder by themselves. Normally, you do have to cook a Diels-Alder a bit just to help, breach those rotation barriers that we talked about a couple days ago. But if we go ahead and react this, a little bit tougher because we're going to end up with a bicyclic system. But let's see. So that's one ring there. Oops. Yes. Okay. So if you do end up reacting these, you do get a bicyclic system. So here's our new. This is our new sigma bond between them. So we're gonna have that there. Those are the two carbons that are connected to the. Oh gosh, those carbons are where the single bonds that are new are attached to. We're trying to say that again. So that's kind of the formation there. That's this bond here. That's the original one I circled. So we're going to be forming two bonds, as we know, kind of over there. So that's if I were to kind of redraw this one as blue, that's this bond here, which I've now just destroyed my molecule. But just so we can see kind of how these are connected. So our two new bonds are circled. Those are our two new sigma bonds. And that kind of light blue bond there is the site of the attack. So where the dienophile, in this case one of the cyclopentadienes, has reacted with the cyclopentadiene. So normally, the reaction arrows are the same, right? As normal, though we do end up with this bridgehead, or this bicyclic compound, because we're putting two cycles together. So, fun stuff. It turns out, though, as we love having bicyclic compounds, when we do react cyclopentadiene, which is very common because it is so reactive towards Diels-Alder, if we want to react it, we typically have to kind of clean it up because it's automatically just going to dimerize by itself. It'll just react with itself and make this bicyclic compound that we can no longer do a Diels-Alder with. If you heat this one up enough, it'll go back into your cyclopentadienes. Remember, we saw that the entropy effects do take over the thermodynamics, so it will break apart again if we heat the crap out of it. And so if you want to do a Diels-Alder with cyclopentadiene, you have to kind of freshen it up because it will react by itself and therefore become non-reactive anymore. So you have to kind of heat it up to get it to go back to cyclopentadiene. Alrighty, let's take a look at some reactions with cyclopentadiene as our diene. We're going to see, just like before, when we have a bicyclic system, we're going to introduce some interesting enantiomers into this. So again, I'm going to kind of draw our six-membered ring with the bridgehead. That's part of the cyclopentadiene. This bond here is our old dienophile. So again, the light blue one is the single bond from our dienophile. And we have two options here. We can end up with our substituents of the dienophile in what's called the exo position, or they can be in the endo position. So either pointing up or pointing down towards the bridge, towards that bicyclic part there or away from it. This one is called endo. And we're going to see that endo is drastically preferred over exo. In most cases, you will only get the endo product rather than the exo product, so where your substituents are pointing down. And how that comes to be is if we kind of think about the transition state of how these two might react. So again, a little bit more, tougher to see perhaps with a cyclic system like this, where our cyclopentadiene is cyclic already. But if we kind of look at the transition states, we can see that this can kind of approach in two ways. So, since these are both planar, I'm just going to put our cyclopentadiene on top, and we can look at the position of the kind of dienophile's substituents as it reacts. So it has two ways to react. So it can react where our electron withdrawing groups are kind of pointed away from the cyclopentadiene, or we can have it where they're pointing towards it. Okay, that's way too close. Let me try that again. Your dienophile, it's okay, whichever way it likes to go is fine. We're going to see, though, if we remember what double bonds are, they're made of p orbitals, right? Those are kind of up and down. We're going to see we're going to have some kind of like nice overlap here if we have those carbonyls kind of close to... Okay, I just made this really impossible to see with all that blue. Okay, let's get rid of it. We're going to get rid of the orbitals, and I'm going to just kind of draw directly on it. So we see here that we have a pi system on top of another pi system. Pi-pi interactions are favorable. Perhaps you remember like benzene stacking and all that from way back then. In here, we have no pi stacking here. So pi stacking is when kind of you have p orbitals that are participating in a pi bond close by each other. They can kind of overlap favorably. And so you get some pi-pi overlap when you have your substituents pointing towards your diene. That is a favorable interaction. In this case, you have no pi overlap. So just because if you see they're pointed away, they're not going to be able to kind of interact. The carbonyls can't interact with the cyclopentadiene. So there's going to be a preference for kind of pointing your substituents towards the diene. And if you can imagine how this is eventually going to react, is we're going to be making... I'm sorry, not that carbon. Let me erase that. No, go away. There we go. We're going to be making a bond here. And if we are going to do that, we're going to end up having our kind of carbonyls here. They're aldehydes. Those are going to be kind of underneath the molecule, which ends up, if you kind of redraw things, we see that we have... Let's see, what other colors can I use? We have our bridge carbon, the one that's going to form that spike in our product. That's this one here, the green one. We're going to see that that's going to be on top, and the carbonyls are going to be kind of on the opposite side, which is going to lead us to the endo product. So we have kind of those aldehydes are underneath. They're down. They're the opposite side of that bridge. In the other case, though, if we have things on pointing kind of out like that, as we end up making this bond, they're just going to keep sticking out as it. So they're still going to end up kind of pointing the same side as our bridge. And as a result, we're going to have them pointed kind of up, and those are going to be your exo product then. So suffice it to say, what you want to take away from this is that you're going to end up with the endo product if you use cyclopentadiene as your diene. And the endo product is the one in which dienophile substituents point down when you draw this. So you can draw it exactly like drawing here. You have your 6-membered ring with your bridge carbon, and you just got your substituents pointing down. And so you can just work with it that way. So endo product is going to be preferred because of the transition state that has some pi-pi overlap. And the exo product generally is not. Alright, even though you might be thinking, well, we have axial endos, but equatorial exos. The exo product is technically thermodynamically more favorable, but these typically are under more kinetic control, so you look at the transition state, what's the better kind of transition state or intermediate state, and that's going to be the one for the endo product. So here you're going to always pretty much get endo. Alright, so that means point your substituents down, away from your bridge carbon. That's the takeaway there. Alright, so fun stuff. Shall we take a look at how the molecular orbitals fit into this? Did you really think we were going to be done with those lovely drawings? In fact, let's let me just copy paste some of those lovely drawings we did a couple days ago. Where are we here? I think it was the day before that. Let's see. I think this is what we're looking at here. Is this the one with all the orbitals? Yes, it is. Okay. I'm going to just copy some orbitals so I don't have to redraw them. But we're going to take a look at the orbitals and how they are interacting here. So give me a sec while I copy these over. We're looking at... here we go. Okay. I'm going to just copy the HOMO here. It's something we've already done before. So I don't have to redraw it all. And back to our current one. Okay. So, if we want to think about how this is going to actually work in terms of molecular orbitals, how this reacts, how a Diels-Alder reaction takes place, this is the HOMO of our diene, right? This is just of a general diene. So if we're just looking at any diene, it's going to have a HOMO that looks like this, where we have the one node, we've got our kind of two separate sides of this orbital. If we, I'm sorry, this is the HOMO. So of, say, ethylene has 2 pi electrons. It's going to have just kind of 2 states. It has 0 nodes and 1 node. Let's see if I've drawn these correctly. I hope so. If we look at ethylene, it's going to have its electrons normally in the lower energy orbital, right? It has this higher energy one that is unfilled. So this is the Lumo of ethylene. Ethylene, just that 2 carbons. Let's draw them with the H's so we know what I'm talking about. 2 pi's only. If we want to see how these are interacting with each other, what we can do is understand that the electrons are going to be moving from your electron-rich species, which is the diene, to your kind of electron-poor component, which is going to be your dienophile. Often remember your dienophile has electron withdrawing groups. Oftentimes your diene has electron donating groups. Your diene is more electron rich. and your dienophile is electron poor. And again, this is just our LUMO of the dienophile. It's empty. But we can see here that if we are going to react these, notice that when we react them, we're going to be reacting kind of the outermost orbitals. So remember that, if we're to look at this molecule, the orbitals would look like this for the HOMO of the diene here. So we have kind of two distinct double bonds, and they're arranged kind of like this, where we have the orbitals inverted after one node in the molecule. And we can see here that this would be our dienophile. It's LUMO, it's unoccupied orbitals. And so we can see here that we're going to have the blue sides of our HOMO interacting with the blue side of our LUMO, and the opposite case for the green side on the other half of the molecule. And so that's how this reaction is able to work, is that you have electrons from your highest occupied orbital, your highest energy orbital, are reacting with the unoccupied. They're going to be donated electron density into that unoccupied orbital. And then as a result, you can then rehybridize these into sp3-1. So they're p orbitals, right? But then we can overlap them and then rehybridize. I don't know how to spell rehybridize. Let's try this again. Rehybridize. Again, this is just why this reaction works. Is that you'll get nice overlap between your HOMO of your diene and your LUMO of your dienophile. And we would therefore call this one kind of allowed by the orbital symmetry. So the orbitals will allow us to conduct a 4+2 cycloaddition, where we've got a diene and a dienophile. That'll work. This explanation also will tell us why we can't do a 2+2 cycloaddition under the same conditions. If we take a look at, these two, let's see why this reaction doesn't work. You can't just say, I'm going to heat this up and I'm going to make a cyclic compound here. The reason it doesn't work, if we take either one, we can say, aha, well, if we want these two to be able to react, they're the same molecule, right? They're both ethylene. So we can say that the HOMO and the LUMO are going to interact. They have the same HOMO and LUMO because they're the same molecule. But we see here, aha, we've got green and green, that's good. But here on the other side, we have green and blue. So that's a no-no. Doesn't matter which one I put on top, by the way. If I had done the same thing up above, I would get the same answer here. If I put my LUMO on top, you'd see I'd still get favorable interaction. The green one would be on the right, blue one on the left. We'd get that to work. Here, we end up getting a mismatch of orbitals. One of them, yeah, it's fine. The other side, though, doesn't work. And so, this is what's called a symmetry forbidden process. So you're not going to get two ethylene molecules to cyclize together using heat. You're not going to end up doing a kind of cycloaddition reaction between these. So that's the reason that you don't see that. So it works with 6 pi electrons. It does not work with 4 pi electrons. So you need some multiple of 6 to get a Diels-Alder to work, or just in general a cycloaddition reaction. All right. How is that feeling? Terrible? We hate these orbitals, perhaps? Don't worry, these are more for kind of explanation purposes. So this is explaining why this reaction is allowed to happen, why we can get our cyclohexene out when we put these two together, and why we don't get a cyclobutane when we put these two together. So, just more kind of background and theory here. Okay, so because your orbitals overlap in a bad way with your 4-pi electron system, you are not going to get a 2+2 cycloaddition here.
So we just need more than 4 to make it.
Yeah, 6 is good.
6.
You can also do it with 12, but we don't typically see too many 12-membered rings, just because chances are you're going to have other stuff happening. You'd probably, if you have 12 pi electrons, you'll probably have 6 of them undergo their own Diels-Alder, and then the other 6 will probably undergo their own, rather than trying to get the geometry for 12 to work out properly. If you had 8, you'd also have problems. You would not be able to work that out. 6 of them would probably do their own thing, and the other 2 pi electrons would just be kind of left by themselves.
What did the 6 look like again?
Sure, let's take a look. So we're always kind of looking at the end orbitals because that's where our bond is going to be forming. I'm going to just erase, or I'll move this somewhere else. Just move it up or something. So if we look at these orbitals, describe this particular molecule, the diene here, where we have 2 distinct double bonds that are separated by a node. I'm going to erase, oops. Just erase this for now. With our Lumo, we're kind of just looking at this guy. So we're looking at our kind of outermost orbitals to be interacting together. So in order for this bond to form, as this reacts, we're looking at kind of the outermost orbitals and seeing how they overlap with each other. And we see on both sides we have green and green and blue and blue. So they're in phase with each other, and that's going to make our single bonds as we go.
Oh, thank you.
Mm-hmm. And so if we look at the same thing with this and this, we see, okay, well, this time they're not overlapping properly, and so this reaction will not happen. Okay, what was I going to say about this also? No, we're good here. All right, let's look at another case. Remember, if we decide to give kind of light energy instead of thermal energy, we can get that ethylene to react with another ethylene. But we can't do it with heat. We have to do it with light. And the reason for that is, remember that if we have our kind of, let me copy those orbitals. Okay. So for ethylene, right? Ethylene, just a single molecule, has these 2 molecular orbitals. Oops. It's got 2 molecular orbitals. It's got 2 pi electrons. They're normally kind of held in the lower energy orbital, right? If we zap this with some light, so that's just, don't I have yellow on this? Yeah, there we go. Impossible to see. Okay, if I blast this with some light, rather, let me draw the arrow pointing to the electrons. That's going to promote one, right? When we give things light energy, they end up promoting electrons to excited states. And so what we can see here is that we will promote one of our electrons to the excited state. I'll just copy everything here. And so while this was our original HOMO for this molecule, once it's in the excited state, though, we have now a higher energy molecular orbital. So this becomes our new HOMO for this molecule. We've promoted an electron to a higher energy orbital. We now have a new highest energy molecular orbital, or highest occupied molecular orbital. And so now that we've given it some light, now we're going to end up reacting these two together. So I'm gonna just copy this. Okay, so this is now our excited one. This is our regular one. Getting rid of our light beam here. We don't need that anymore. We now have, this is the HOMO from our excited state molecule. If we take a look at a different ethylene molecule, we now see that the same orbital is the LUMO for the other ethylene. And so now if we take those two and put them together, if we want to see how those are going to overlap with each other, we have apparently the bad things because I can do this either way, but I've drawn them where I have the green up on one side. This is these can be drawn the other way if I decide to, right? It doesn't matter because this molecule can just flip around. Like, I've drawn it, here's C1 and C2 in this molecule. This molecule can just flip around where I have C2 on the left instead, right? So, I'm not just making this up, don't worry. I can actually switch the colors with these because there's only one set of p orbitals here. So, we can, as long as they are still kind of disjointed, so the lower orbital has to have green on top or blue on top, either way, same thing. I could flip that over. I could say it's blue on top here, and green on the bottom. That's totally fine, no problems. Those two are the same thing, right? I just kind of arbitrarily chosen to put blue on top. But if I just flip this molecule over, now the green's on, or whatever, they're the opposite, right? But they're the same, they're just flipped over. I can do the same thing with the LUMO. So I've drawn it where I've put green on the top left, green on the bottom right. As long as those two are on the opposite corner, that's the important part. So if we kind of just redraw some things, I can't redraw it for the last one, because if I do that, I'm still going to have the same problems. If I try and overlap, I'm going to have these ones still working. I'm going to have these ones still not working if I try and switch things. So we're not violating any rules here. I'm just, I've arbitrarily decided to put green on the top left in one. Doesn't matter, because as long as they are opposite sides of each other, that's what matters. So now we can see happy overlap happening here. And so we're going to get a successful reaction. So just geometry. If I had flipped, this thing is just two carbons, it's rotating around, right? Or it's spinning, it's not rotating. So totally allowed for this to happen. If I just rotate around this axis, and we can get them to overlap happily, and so we will end up getting our reaction to happen if we use UV light to promote an electron to a higher energy orbital. All right, I realize that might be a little bit confusing. Let's take a look at it in either case here. So even if I switch the LUMO orbitals up here, or switch the HOMO ones, it doesn't matter. I can switch both of them. If I did the blue ones up here instead, and the green ones down here, we're still going to have the same problem. So if I also switch the HOMO ones, if I say, okay, I'm going to put the blue on top now and the green on the bottom, those are arbitrary decisions. What matters is that in the HOMO, the blues are on the same side, and in the LUMO, they're on the opposite side of each other. So we're still going to end up with the same problem if I switch the orbitals here. So I'm not doing anything crazy by flipping this set of orbitals upside down. Totally allowed to do that. And so we have our kind of empty LUMO here. We've got our HOMO here from one excited ethylene molecule. They can now react together. And so with the UV light promoting an electron to a higher orbital, that changes things and will allow us to do this reaction. So just understand that if you wanted to do this, you could do it with light, but you cannot do it with heat. So if you want to do a 2+2 cycloaddition, this is the most important little bit here, cycloaddition. You've got to give it light. I'm going to write that as H nu. You must use light energy instead of heat energy. And so we're going to see here that, just kind of in summary, for cycloadditions, this would be a 4+2. So 6 total pi electrons. You can use thermal energy to get this to react. If you want to do a 2+2 cycloaddition, you need to use UV light. I'll just indicate that once more. When I say H nu, that means light. So, and if you try and do the opposite process, if you try and do a 4+2 with light, you're going to end up not reacting. If you try and do a 2+2 with heat, it's not going to react. So we need things to kind of excite things in the 2+2, and we cannot have that happening in the 4+2. If you tried to do that, you're going to see that it did work normally with happy overlap here. But if we promote an electron to a higher energy orbital in our diene, we're going to end up now having a different HOMO that's going to have, in fact, the opposite symmetry. That's going to give us problems. We're not going to be able to work with that. So this is the big picture right here at the end. If you're going to do a 4+2, use heat. Again, sometimes that just means room temperature. Doesn't need to be like actual heat. And if you want to do a 2+2, you're going to have to use UV light to get it to happen. All right, so this is the big picture here. All right, so that's kind of our last little bit. Alrighty. Questions on that stuff? If you try and use the opposite one, it's not going to work. So it has to be heat for one, light for another. All right? All right. Yeah. Question?
Oh, so and it's light because it gets it to a higher energy.
Yeah, it's got to go to a higher energy one because the higher energy one will overlap nicely.
Oh.
But the other ones, you just want the ground state. Alrighty. Cool. Let's talk about electrocyclic then. So that's cycloadditions. Those were, you're getting rid of 2 pi bonds, you're making 2 sigma bonds. Let's talk about electrocyclics. And again, we're going to kind of evaluate 6 pi electrons versus 4 pi electrons. We're going to see that these would typically follow the form. There's 6 pi electrons there, or I should draw that with better geometry. There we go. This sort of reaction will end up giving us, we had 3 pi bonds before, we're going to end up with 2 pi bonds, and we are going to end up making 1 sigma bond. So this is an example of an electrocyclic reaction. You can do it with 4 pi electrons as well. A little bit harder, just because things are going to end up being a little close to each other. You make a cyclobutene in one or a cyclohexadiene in the other. And we're going to see that with these, light and heat, again, are going to be kind of our modes of making these things happen, but we're going to have different things happen. They can both, in this case, they can both react with heat or light, and they're going to react in different ways. With a 6 pi electrons system, we're going to see that if we had some substituents on here, it's just going to change the stereochemistry. I'm going to just make this like kind of super obvious that I've got methyl groups that are kind of on the opposite sides here. If I give this thing light, when we make our 6-membered ring, we're going to end up getting these cis to each other. Both on wedges, plus, I mean, you'd get the enantiomer as well, right? Yeah, you would. If you try and use light, you're going to end up getting them trans to each other. And so we get some kind of additional accessibility to our toolkits here by doing this. And if we want, we can go ahead and break this down. We're going to see if we break the top one down that we used heat to make the cis kind of relationship between those methyl substituents. We're going to end up breaking it down. And if we use heat on the one that we originally used light on, we are going to get the same product if we reverse this reaction. But this time now, they're going to be kind of on the same side. So those methyls originally were pointing away from each other. If I react that with heat, I get them cis to each other. If I react that with light instead, I'll get them trans to each other. And then I can go ahead and do the opposite, and then I'll end up with a molecule that now has them pointed the same direction, the methyl groups. So I can kind of isomerize my double bonds. Remember, double bonds can't rotate, but we see here we have essentially a trans relationship in the first molecule and a cis relationship on the rightmost molecule, and we can do that using either one of these. These are all technically equilibrium, just so we know. So if you want to mess up your molecule, you can just throw heat and light at it and watch it go crazy. But we can investigate why this happens. We're going to see with 4 pi electrons, it's going to be just the opposite, like it was before. We're going to see that if we put the heat on it, we're going to get the trans relationship. Remember, these methyl groups are cis to each other here. They're trans to each other here after giving light to our molecule. We're going to see the opposite case with our 4 pi system, which I've drawn way too close, and now I have to move it all down. 1 sec. All right, I'll stay on this for a bit, so as there's a lot of molecules here, so I'll stick on this for another minute or so. So, putting heat on it, you get cis. Putting light on it, you get trans. We're going to talk about how this works in terms of molecular orbitals. We're going to see that they're going to, in an electrocyclic reaction like these are going to end up having the molecule or the orbitals rotate onto each other, and there's going to be 2 ways that they can rotate. But we'll get to that in just a little bit here. So I want you to be able to kind of see these molecules so you can draw them. Alrighty. So just like Diels-Alder, these are reversible. You know, to put more stuff on them. If you heat them extra, you can get them to go back. Same old thing. Alright, let's take a look at the 4-pi system. We're going to see if we give this heat, we're going to end up with, this time, a trans relationship and the enantiomer. If we give it light, instead, this time we'll get cis. So in this case, with the heat, we get the trans isomer, and here we get the cis isomer, a relationship of those methyl groups. Before they're pointing up and down, they're opposite kind of side. Guess what's going to happen if we do the opposite process to these? We end up getting, we'll end up moving one of our methyl groups, just like before. So now they're both kind of pointed down. And so we'll just, again, isomerize our diene. So same idea here, but just like with the 6-pi versus 4-pi electrons with cycloadditions, we see light and heat do different things with these. And it's exactly the same reason as before. It's because light will promote into a different orbital, and that orbital will react differently than the just plain old ground state orbital. All right.
Sorry, Professor.
Yeah, what's up?
Quick question. You mind scrolling up just a little bit to the last one we did?
You want to see the top one again?
6-pi one. 6-pi one. Yeah, I just wanted to see which one you put as trans and cis.
Yeah, sure. So the cis one is the heat, the one produced by heat, and those two methyl groups end up pointing the same direction, so that'll be the cis. And then if you use light instead, you're going to end up with the trans, so the opposite case from the 4-pi. So.
Okay, I got it.
You good? Okay.
Yep.
And down we go. So again, with this, I'll leave it for a few seconds while we work on this. So we're going to see with these, we're going to be looking at the HOMO and LUMO like before. Although technically we only need to look at, because these are only one molecule, they're intramolecular, right? So we only need to actually look at the HOMO of all of these. Though we see if we want to use light, we are going to look at the LUMO because that becomes the new HOMO. So, all this terminology. Let's look at that let's look at the HOMO of our 6-pi electrons. If we remember, the lowest one had all 6 pi's on the same thing. The next lowest orbital had one node that splits 3 and 3. And the HOMO, which is the third orbital for a 6-pi system, has 2 nodes. And so we have, that's how they're going to be split in the HOMO for a 6-pi single molecule. Like this. What we're really looking at here, though, is we're going to be, because if we take a look at this molecule, we're looking at, if we say this is carbon 1 and carbon 6, for just the things that are part of that pi system, that's where the bond is going to be made, right? That's the bond that's going to be formed in our electrocyclic reaction. And so we're really only looking at these 2 orbitals. We're looking at the 1st and 6th ones. We call these, by the way, frontier orbitals. They are the ones on the ends. And so if we want to now kind of twist this, if I want to make this a little bit easier to see, since we know we're going to make a 6-membered ring, if I kind of say, okay, well, let's look at the orbitals this way. So we know we have green up there, green up there. And so I'm only drawing the orbitals on the ends. We don't care about the rest of the orbitals for this one. If we want to see where the methyl groups are, by the way, we have our methyl groups, they are pointed kind of away from the molecule, right? In that first example, they are pointed away from each other. They're both pointed away. So if we're just looking at this from the side, they're both pointing kind of out, away from the molecule. If we want these two orbitals to overlap in order to have that, ideal symmetry, we're going to see that whatever way we kind of need to rotate this orbital, so let's say we rotate this one this direction, we need to rotate the other one the opposite direction. Do we see that? So we need both greens to overlap. I could have overlapped the blues instead. Doesn't matter. What matters here, though, is that this is what's called a disrotatory process. They are rotating the opposite direction from each other. So one of them is going to rotate clockwise, the other one's going to rotate counterclockwise in order to have that nice, favorable overlap. So one goes clockwise, the other counterclockwise, and we're going to end up kind of rotating them there. If we do that, if we rotate those, if we've now rotated so now that we have our green bits overlapping, notice that this methyl, if I rotate the left one clockwise, that methyl ends up going up. Do we see that as I rotated everything? The methyl group goes up. As I rotated the right one counterclockwise, we end up getting our methyl up as well. That is a cis relationship that we have there between them. And so, if we go ahead and just kind of peek back to our previous one, we saw, aha, if we do a plain old thermal reaction using the regular HOMO, we get a cis relationship of our methyl groups, of our substituents. And so as a result, we have a nice cis pattern here. Okay? This is a disrotatory process, meaning the orbitals are rotating in different directions. We end up with the cis product. Six-membered ring with two methyl groups pointing up in order for this to work. Does this kind of make sense? We have to rotate our orbitals so that they can overlap together in order for us to have this intramolecular reaction to happen, and as a result our methyl groups are both pointing up. If I rotated the opposite directions, they would point down instead. That's the enantiomer, right? If they're both on dashes. The point is the relationship is still cis. They're both the same side. So if they're on the top side or bottom side, they're still cis to each other. So whichever one. All right. Shall we look at the... Yeah. Question?
Oh, so that was just an explanation of how the 6
yeah, why the 6 one ends up with a cis product. Yeah.
Okay.
Do we want to look... Let's just look at 4 pi now, and why that ends up with the trans product. So the HOMO for the 4 pi looks like this. This is our HOMO for 4 pi system. If we just take a look at the frontier orbitals and kind of... I'm going to kind of draw it the same way where it's just kind of like whatever. With our methyl groups, we originally had them pointing the opposite sides, right? They're pointing out. So it'll be just the same as before. If we take a look at those orbitals, we have blue on the bottom, blue on the top, green on, and they're on the opposite sides of each other, right? So if I'm looking at just our outermost orbitals, that's where the chemistry is going to overlap and form that new sigma bond. if I want to rotate these, let's say I want the green ones to overlap, I'm going to need to do, in this case, I'm going to have to rotate both of them clockwise in order to get this reaction to happen. This is what's called is it conrotatory? Conrotatory, yeah. It's just like before, conrotatory. They are rotating the same direction. These are both rotating clockwise. I could choose to rotate them counterclockwise and overlap our blue orbitals. Either way will work. We end up with, since I like the green orbitals today, we end up with our green orbitals overlapping, which will form our new sigma bond. And in this case, this methyl has rotated up, and the other one has rotated down. Do we see that? As these rotate, they're both rotating clockwise, and as a result, one will end up, one will end up down. These have a trans relationship to each other. And again, if I chose to overlap the blue ones, I would end up with the enantiomer of this molecule where it's the left methyl down and the right methyl up. But they're still trans to each other in either case. So this is just to kind of determine the stereochemistry of your electrocycle. All right, let's just kind of, it's the same idea for if we use UV light, we would just have different orbitals. We're going to see that it's conrotatory for 4 pi with thermal. It becomes disrotatory for 4 pi with UV light. They just switch the opposite. So let's take a look at kind of just like a little table here. So if we want to use heat with these, this one is conrotatory. We just saw that the orbitals rotate the same direction. They both rotated clockwise or counterclockwise, but they're rotating the same direction. That's con. This one is disrotatory. And if you really felt like it, you could draw the, if you promote an electron to the next orbital, what was the LUMO, you'll see that it'll just be the opposite process. And so you'll just get the opposite stereochemistry. So for 4 pi, it gave us the trans relationship with heat because they were conrotatory. If we looked at the orbitals from the LUMO instead, with light, that's kind of, we're looking at the HOMO here. And with the light, we're looking at the LUMO, because the LUMO becomes the new HOMO when it's got one electron promoted into it. And so we end up getting different products here. So if we did UV light with the 4 pi, we would end up with cis, because that's how the orbitals would overlap properly. So this kind of is our chart here of what's going to be happening with these electrocyclic things. And so again, if you are kind of, what's the word? Lost about something, you may want to just draw something like this where you're looking at the frontier orbitals, seeing which directions things are pointing to begin with, and then rotating your orbitals properly. Let's do an example. I think that would help us out here. So I'll leave this chart up for now. Or you can just refer to the that kind of schematic we did at the beginning where we took something like this and we decided to make them work out or not. Or we would see which one gave us cis, which one gave us trans through this rotation process. If we try and heat this up, we can see what's going to happen. We have a 6 pi electron system here, 6 pi's. We're going to end up with a 6-membered ring. We're putting heat on it. So according to this chart, that's disrotatory, but maybe we're not too clear on that. So maybe we want to draw the orbitals out. For a 6-pi system, if we look up, the HOMO is the same for every 6-pi system. So we're going to end up with the same color on the top and the bottom of our orbitals. But what's important to note here is that the ethyls are pointing the same direction in this. We could point them either way. I'm going to point them both that way. Why not? So do you see how they're both pointing the same way? In the previous one we had the bottom, we had methyls instead, but this time it's ethyl. We had that one pointing down. We started with slightly different. We started with a slightly different molecule. Where did it go? I guess we looked at this. Okay, there we go. We looked at methyls pointing away from each other. This time they're pointing the same direction. They're both pointing up here. So if you want, we could just cheat and be like, aha, well, we could be like, oh, well, look at here. They're pointing the same direction. If I put heat, I'm going to get the trans product. We're going this way. We can get the trans product by putting heat on this. And indeed we will, but if for some reason you don't remember this schematic, which I get because there's a lot of information, we could do it with the orbitals. We can do it the old-fashioned way. I could ask you as well on an exam to draw the orbitals showing why you get the trans product from heating this. So, what's important here, we know that with heat for a 6-pi system, we need them to rotate the opposite direction so we get good overlap. So, which way will we like to rotate them? Let's do it this way. I like the green ones. So they're going to rotate the opposite direction so that they overlap. If we do that, the ethyl group on the left is going to rotate down. Do we see that? As we rotate that clockwise, the ethyl group gets pushed down. So our ethyl group now is down. Again, I could decide to do the blue ones. I just apparently have a preference for green today. If we look rotating that, the one on the right, counterclockwise, that ends up putting our ethyl group up. Let me clarify that. We now have this pointed up. We see that these are trans to each other. And so if we just draw the product, we'll see, aha, well, we know we end up with this here, and our methyl groups on the back don't really matter. They were just there for some reason. We're going to see our ethyl groups are trans to each other. So we're going to get one ethyl group down, one ethyl group up. I guess I can draw these as actual carbons. No. They're going to end up just being on opposite sides to each other. These are trans to each other. And we would get the enantiomer, right? So we could have the dash being on the top, the wedge on the bottom, doesn't matter. But the point is we get the trans relationship there, if we were to do these. Alright, so that's kind of what we're looking at with electrocyclic reactions. Alright. Any more questions on those? So, is Charmos doing like practice with you guys on this stuff? Is he doing like practice problems and...
Yes.
Yes, okay, good. Good. Then you'll have plenty of practice with this sort of stuff. So I do send him like every day what I've done with you guys, so hopefully he is kind of following through that. Alright, let's talk about our last pericyclic reaction then, which is called a Sigmatropic Rearrangement. In this case, we're not having a change in the number of pi bonds or sigma bonds. These are just kind of we're essentially like making the same molecule. So with these, if we go ahead and take a look at this, if we just see what's going to happen, we're going to end up having the same idea. We still have kind of 3 electrons moving here, but we end up, we're going to see in this case we end up with the same molecule, but just rotated. And so that's what this will look like. We're going to see if we throw, say, a methyl group on there. Poof, now we have a methyl group on there. So we have probably made our molecule a little bit more stable. In the left case, we had both double bonds, both alkenes, as having 1 substituent. On the side on the right, we now have 1 alkene with 2 substituents and 1 with 1. So we have slightly improved the stability of our molecule. Just need heat for these, by the way. It's much the same type of idea. This is called, by the way, essentially a 3-3 Sigmatropic rearrangement. And how we decide these numbers is we kind of look at where that single bond is going away. So we do break a single bond in this kind of rearrangement, and we make a new one. So we're kind of looking at where that sigma bond is breaking and forming, and that's along that dotted green line there. And so if we just see, we have 3 carbons here that are taking part in this reaction. That methyl group that's sticking out doesn't actually play any part in this rearrangement. It's just there as a substituent. So we see we have kind of 3 carbons where our top part of this is happening. We have 3 carbons on the bottom where this is happening. That's why it's called a 3-3 sigmatropic rearrangement. We're not going to really see other ones. I mean, there are other types of sigmatropic rearrangements you can have. You can have 3 2s, for example. This is just a 3-3. We have 6 total carbons participating. 3 of them are going to be kind of on one side of the molecule, 3 are going to be on the other. So again, that green line here cuts through where the sigma bond is breaking and forming. So, and we have 3 carbons that are participating in this reaction that are on either side of that line. So again, the methyl group doesn't really count here. By the way, this is also called a Cope rearrangement. Specifically, if all of these are carbon, which generally things are. So all 6 atoms that are taking part in this reaction are carbon atoms, and so we can call this a Cope rearrangement. And we see that, for example, this particular one is going to end up with about an 85% in this form, where we have the doubly substituted double bond, and the other 15% might be in this original form. So this is something that's continuously ongoing, so some of these are breaking and going backwards. So it's a smaller equilibrium pushing the other way. And so it's just called a Cope rearrangement. We can rearrange things to make them happier. For example, let's see what's going to happen here.
Sorry, what did the percentages represent again?
The proportion of how much each one is. So if you just had one of these, it's going to immediately just kind of do this rearrangement. And so there's kind of, it's not quite resonance because we're breaking and forming single bonds here, but 85% of the molecules will be on that right kind of form, dare I say, and the other 15% are going to be the left molecule. So there's a dynamic equilibrium here happening. So these molecules just spontaneously do this rearrangement. And so at any given time, if you just take a snapshot, 85% of them are going to be in that right form, and 15% are going to be in the left form. So that's all.
Okay.
It's just that they are happen to be arranged in that way. So if we see how this might rearrange in cope style, remember, if we are going to do a cope, we are going to form a single bond in between the two double bonds. We're going to move one of the double bonds down, and we're going to break a different sigma bond. And so if we were to look at this molecule, let's see how many carbons it has. We see we are breaking that bond between carbons 3 and 6. And we are now forming a bond between carbons 1 and 8. So we're getting rid of that kind of butane bit there, cyclobutane. We're breaking that cycle. And we are going to end up now with a new bond between 1 and 8. So we're going to end up, in this case, with an 8-membered ring. And we're going to have 2 double bonds here. So those double bonds are going to be carbons 2 and 3, and then 6 and 7. So let's just number these. There we go. So we're going to see that our new double bonds are between carbon 2 and 3 and carbon 6 and 7. Do we all see how this kind of worked? We essentially took out this one, and we made this one. And then we also moved some double bonds around. So I'm going to just undo that so we still have, oops. Okay, so good idea to number your carbons if you're looking at rearrangements like these. And that'll help you kind of figure out what the product is going to be. So do we see how we got this? We broke one sigma bond, formed a new sigma bond. We broke one that was between 3 and 6. It used to be right here. And we have formed the one, this is the new sigma on that side. We broke the bond between 3 and 6, that was that cyclobutane. And then we formed one between 1 and 8. And then we moved our double bonds. So,
kind of a quick question.
Yeah.
Might be kind of stupid. I labeled the one where the 8 is.
Okay.
Just started from there.
Yeah.
But I still got the double bond from 2 and 3.
You'll get the
and
right.
6 and
Yeah,
7.
if you number the other way, it doesn't matter. You'll get the same thing. So.
Okay.
I mean, you still have the double bond. Oh my gosh, just destroyed this. You still will end up, if you number it the other way, you'll still have the same thing. So.
Okay.
If you see 1, 2, 3, so notice you still have it between 2 and 3.
Yeah.
5, 6, 7, 8. Yeah, it doesn't matter. There's no preference for numbering it one way or another. You still have the double bond between those two numbered carbons, 6 and 7 and 2 and 3. And then 1 and 8, you still have the new sigma. So this one we're probably going to see that it's probably going to go almost all the way to form that 8-membered ring, because 4-membered rings suck, right? Nobody wants to be a 4-membered ring. There's too much ring strain there. 8-membered ring is a little bit more stable, so probably going to have a higher proportion that end up this way. Okay, so if we just throw a little bit of heat at this, we'll probably get it to pop open into now an 8-membered ring. Yeah, let's do one more for this. Okay, let's see what's going to happen here. By the way, the reason we know these are going to undergo a cope rearrangement and not something like an electrocyclic process, I mean, they could, but we're going to see typically with electrocyclics, especially if it's a 6-pi system, you need a third double bond here. If we had something like this, which could happen, we could have that, it's probably more like it's going to undergo an electrocyclic reaction here if you've got 3 double bonds. If you just have the 2, you might be tempted, well, we could have a 4 pi kind of reaction happening, an electrocyclic reaction. But if you do that, you're going to end up with like some terrible, horrible structure that would just never want to exist. You're going to end up with like somehow this like 2 double bond thing here. It's just going to be a mess. It's a disaster. So I don't know what kind of horrible ring strain this thing has. It is unlikely to undergo an electrocyclic reaction if you have a 6-membered ring already, like this. Same thing with the previous example. We had kind of a 6-membered ring in the making. It would be unlikely for us to try and form a second 4-membered ring. So remember, an electrocyclic doesn't make any, or it still has the same number of carbons within the new ring. So a sigmatropic, you can go crazy. As you see here, we somehow got a now cyclooctadiene out of this. If we were to try and do an electrocyclic reaction, a 4 pi electrocyclic 2 plus 2 thing, we would end up with, instead, we would end up with this product instead. Where would our double bond be? Where would the double bond be? Regardless, we're going to end up with some disaster of a molecule. As you can see here, we now have like 3 4-membered rings, which has just totally destroyed this molecule. So, don't do it. So, chances are you're more likely to undergo a cope than a 4 pi electrocyclic reaction. Anyways, let's go ahead and look what's going to happen here. So, as always, we're going to form a sigma bond, move a double bond, break a sigma bond. If we do that, draw the rest of our molecule. We have a double bond now here. Oops, that's a single bond. This should be our new molecule with this. So, do we see how the arrows are pushing here? So we're going to make a new sigma bond. We're going to move our double bonds and break an additional sigma bond. Which of these do we think is more stable? The left one or the right one?
The right one?
Right one, for sure. Right. It's got much more substituted double bonds. So right one is going to be more stable here. So again, these are reversible reactions, but again, they're going to favor one side more than the other. So equilibrium-wise, both of these would prefer the product. So more stable. Why is it more stable? Because it has more substituted double bonds than the original molecule. Okay, but if we really wanted, we could say, aha, we're going to, break something, and now we're going to end up with our original molecule again. So, if we try to do another cope rearrangement here. Alrighty, one more. This is the Claisen now. In this one, it's essentially the same thing, but we have an oxygen present. If we have a vinylic or an allylic ether, these tend to undergo Claisen rearrangements much the same way. It's the same thing, same reaction, but we now have an oxygen in there, and so it gets a fancy new name. And so we end up with this molecule. And this one is going to be kind of even more favorable than the previous, that first one we did with the 85-15. That's actually with the substituent on it. the actual cope is going to be like 50-50. Like, right, if I take these carbons off, it's 50-50 because they're the same molecule, right? Nothing crazy there. This one, we actually do have a preference about 90% here and 10% here. Because a C double bond O is much more stable than having these allylic ethers. So carbonyls are going to be preferable because it's just more stable than a carbon-carbon double bond is. So carbonyls are more stable than alkenes are. So we're going to see here that that's going to be the reason that this is preferred. All right, so typically you'll have an allylic and vinylic ether that this is happening on. This is the kind of allylic part. This is the vinylic part. Vinyl, remember, means it's directly attached to the double bond. Allylic means one carbon away. If you have a pattern like that, you're very likely going to undergo a Claisen rearrangement. If we want to look at another example, we have a vinylic bit here. This is our vinylic bit. We have our oxygen directly attached to a double bonded carbon, and we have our allylic bit here. I'm going to just rearrange this molecule, and I'll show you how we can have the Claisen happen here. So same thing there. And I'm just going to move our double bond upside down so we can see more clearly the double bonds that are going to be participating in this. So, yeah, this will work, and then we'll, actually probably more likely to happen is this is going to break there. We're going to more likely happen that way, yeah. If we do that, so remember the point of this is to form the carbon-carbon double bond. So, or sorry, carbon-oxygen double bond. We now have this here. And what's likely to happen now, do you remember this word? Tautomerize. There we go. Do you remember what tautomerization is? Is that a word that is somewhat vaguely familiar?
No.
No? Oh dear. Okay. Well, suffice it to say there is this... We'll talk about tautomerization next time. So tautomerization is a process where we are going to kind of basically switch a double bond and a hydrogen. It's just a way of stabilizing things, and we're going to see that this is... forget it. Tautomerization we'll talk about next time. So, just suffice it to say for now, when you have a vinylic and allylic system ether, you can get this Claisen rearrangement. In this particular case, it's much more stable to tautomerize because you're going to make a benzene. Benzenes are ideal, but we'll deal with that later. So, all right, let's talk about that next time then. So for now, we're good. We have just UV vis to cover because Thomas wants me to do that. So we'll go from there, and then we'll talk about aromatic systems. And I think is that. Let me just check our syllabus real quick. Are we like... When's our first exam? Is that next week or is it the week after? Anybody know?
It's the week after.
It's next week?
On the 27th.
27th.
27th. Oh, okay, so then we've got time. So, because I do want to put aromatics on your first exam, but that's an easy chapter. Much easier than this one is. So, cool. We don't need this. Okay. Awesome then.